Let's continue investigating entanglement-based quantum key distribution. Consider this quantum state just before measurement. This is a special case of this general quantum state before measurement, where Alice's public bit and Bob's public bit are both equal to 0. This means both of these Hadamard gates are deactivated. By convention, the red qubit on the left belongs to Alice, and the blue qubit on the right belongs to Bob. So we can think of this as Alice applying the identity operator to her qubit, and Bob applying the identity operator to his qubit. So that means that both Alice and Bob will measure their qubits in the Pauli Z eigenbasis. Now, because we've seen that this is the same as the action of the identity operator, this means that this quantum state will remain unchanged. Here we have a Bell state, which is specified by two classical bits, zeta and xi. We can write this Bell state in this format. Observe that there is a normalization coefficient of 2 to the power of minus 1/2. We can also write this normalization coefficient as 1 over the square root of 2. Now observe that over here we have the state 0 xi plus minus 1 to the power of zeta times the state 1 xi bar. So what is zeta doing in this expression? When zeta is equal to 0, that switches off this minus sign. But when zeta is equal to 1, this minus sign is switched on. What about xi? What does xi do in this expression? When xi is equal to 0, xi bar is equal to 1. So in that case where xi is equal to 0, we have the state 0, 0 over here, and then we have the state 1, 1 over here. So that means that if Alice and Bob perform measurements of this state, they're guaranteed to get the same outcome. So they're guaranteed to either both get 0 or either both get 1. So we can write that as Alice's secret bit is equal to Bob's secret bit. And then we XOR with the value of xi, but in this case, which we are examining, xi is equal to 0. So that does not change the value of this secret bit. So in that case, we have identical values over here. Another way of thinking about this is if we compute the expectation value of Pauli Z tensor product Pauli Z, we're going to get plus 1. So this is because xi is equal to 0. We're going to get plus 1 over here. That means we have identical values. So if we repeatedly prepare the same Bell state, and then Alice and Bob measure their qubits in the Pauli Z eigenbasis, then this expectation value is going to be plus 1. So we have just discussed the case where xi is equal to 0. But what about the case where xi is equal to 1? If xi is equal to 1, then over here we have the state 0, 1. And over here we have the state 1, 0. So this bar tells us that we have to flip the value of xi over here. So if we have the state 0, 1 and then the state 1, 0, that means that we're guaranteed that Alice and Bob will have the opposite value. So that means that Alice's secret bit is equal to Bob's secret bit XORed with 1. So we're going to have to flip one of these secret bits in order to get the same value. Now another way of looking at that is if we compute this expectation value of ZZ, then we're going to get minus 1. So the value of xi over here, that activates this minus sign, and then we get minus 1. So if this expectation value is minus 1, that means that the outcomes are guaranteed to be opposite. So in the case where xi is equal to 0, Bob and Alice are guaranteed to measure the same value. So they're either going to have 0, 0, or they're going to have 1, 1. But in the case where xi is equal to 1, then they're guaranteed to have opposite values. So they're either going to have 0, 1 or 1, 0. And then one of these two participants are going to have to perform a bit flip in order to guarantee that these secret bits are equal. And then they can move on to the next stage of this protocol. And they can either add those secret bits to their shared random secret key, or they can publicly broadcast those secret bits in order to check and see if this pattern is satisfied. So that is a checking procedure which allows us to make sure that there is no eavesdropper, and it also allows us to make sure that the noise is not too high. So that means we can run this protocol successfully. So this is only one case which we have examined here. This is the case where Alice's public bit and Bob's public bit are both equal to 0. So this is a case where we move on to the next stage of the protocol. But let's examine another special case. So this is another special case where the public bits are both equal, but they're not equal to 0. Instead, they're both equal to 1. So let's examine this case where Alice's public bit and Bob's public bit are both equal to 1. In this case, these Hadamard gates are both activated. So Alice and Bob both apply a Hadamard gate to their qubit, and that is done before measurement. Now, another way of thinking about this is Alice and Bob are moving from the Pauli Z eigenbasis, which is the computational basis, to the Pauli X eigenbasis. So now they are measuring in the Pauli X eigenbasis instead of the Pauli Z eigenbasis. So in both of these cases where the public bits are equal, Alice and Bob are measuring in the same basis. So over here, where the public bits are both 0, they're both measuring in the Pauli Z eigenbasis. But now over here, where the public bits are both equal to 1, Alice and Bob are both measuring in the Pauli X eigenbasis. So let's look at this from several different perspectives. First, let's consider the action of these Hadamard gates on this Bell state. So this notation, beta sub zeta xi, that is a shorthand notation for this state, which is specified by the classical bits zeta and xi. So now imagine that we apply a Hadamard gate onto both of these qubits. What is that going to do to this state? Well, it's going to map it to a different Bell state. And in this different Bell state, we're going to have the roles of zeta and xi being swapped. And we will also have a minus sign introduced if both of these classical bits are equal to 1. So what happens to the beta 0, 0 state? The beta 0, 0 state is mapped to beta 0, 0. So it is unchanged. So the beta 0, 0 state is unchanged by the action of both of these Hadamard gates. So if we apply both of these Hadamard gates, we still have the same state, assuming that zeta and xi are both set equal to 0. But what if we have the beta 1, 1 state? Well, then this is going to be mapped to minus the beta 1, 1 state. So the effect of these Hadamard gates is to introduce a minus sign over here. So this minus sign is only activated when both zeta and xi are equal to 1. So these two cases, the beta 0, 0 and the beta 1, 1 states, they are cases where zeta is equal to xi. But what if zeta and xi have different values? What happens to the beta 0, 1 state? Well, that is mapped to the beta 1, 0 state. And what about the beta 1, 0 state? That gets mapped to the beta 0, 1 state. So that is what we mean by the value of zeta and the value of xi, they swap roles. So we could write this expression over here, but we could just swap the places where zeta occurs with the places where xi occurs. So we could write zeta over here and zeta bar over here, and then we can put xi over here in control of this minus sign. So that is what is going on in this expression. So this is one perspective of what is going on in this case. So we're taking that as an inspiration from this quantum circuit diagram, which helped us visualize this type of quantum key distribution protocol in the previous video. So that is what's happening at this stage, right before measurement. So now let's have a look at a different perspective. So in this part over here, we saw that Alice's secret bit is equal to Bob's secret bit XORed with the value of xi. But now, because xi and zeta have swapped roles, we're going to have to put zeta over here. So now we have that Alice's secret bit is equal to Bob's secret bit XORed with the value of zeta. And another way of looking at this is if we compute the expectation value of x tensor product x, then we're going to get -1 to the power of zeta. So if zeta is equal to 0, that means this expectation value is +1. So that means that the secret bits are guaranteed to have the same value. But if zeta is equal to 1, then the secret bits have opposite values. So they're guaranteed to have opposite values, and we're going to have to flip one of these values in order to get the same value. And that corresponds to a -1 for the value of this expectation value. And the way to compute these expectation values is you can sandwich these observables in between a bra and a ket. So imagine a bra version of this Bell state coming in from the left, and then we have this ket coming in from the right, and we can sandwich this z tensor product z or this x tensor product x. And if we do that and evaluate, we're going to get -1 to the power of xi for this case over here, and -1 to the power of zeta for this case over here. So in these two cases, the public bits are equal, so that means we can progress to the next stage in the quantum key distribution protocol. But what if the public bits are not equal? These are random classical bits, so it is also possible that they will have different values. Let's examine these two cases down here where these public bits have different values. So first, we'll have a look at the case where Alice's public bit is equal to 1 and Bob's public bit is equal to 0. So this is the same as Alice measuring in the Pauli X eigenbasis and Bob measuring in the Pauli Z eigenbasis. So Alice applies the Hadamard gate and Bob does not apply the Hadamard gate. So over here we can see 1 and 0. Those are the values of these public bits. So what does this do to this Bell state? It does not map it to another Bell state. So in these cases over here, we were just dealing with Bell states. So we had states of this format. So these are maximally entangled states. But what's happening over here? We no longer have a Bell state. Instead, we have a superposition of all 4 of the 2-qubit computational basis states. So that's 0, 0, 0, 1, 1, 0, and 1, 1. So all 4 of those states are present in this superposition. And the coefficients at the front of all of these states, they are plus or minus 1/2. So here we have 2 to the power -1, that is 1/2. So the absolute value of all of these coefficients is 1/2. And if we take the absolute value squared, then we're going to get 1/4. So there's an equal probability of all of these outcomes. That means there's no guarantee that the secret bits are going to be equal, and there's no guarantee that the secret bits are going to have opposite values. So another way of stating that is that the expectation value of x tensor product z is equal to 0. So we have no guarantees of equality or the fact that we have opposite values. Now let's have a look at a similar case over here. This is the case where Alice's public bit is equal to 0, but Bob's public bit is equal to 1. So Alice is measuring in the Pauli Z eigenbasis, and Bob is measuring in the Pauli X eigenbasis. So again, the expectation value is 0. And what's happening over here with the Hadamard gates? So Alice is deactivating her Hadamard gate. That's the same as the identity operator. And Bob is activating this Hadamard gate, and that means he's applying the Hadamard gate to his qubit. And what does this do to this Bell state specified by zeta and xi? Well, it gives us a state of a similar format. We again have a superposition of all 4 of the 2-qubit computational basis states. So we can see 0, 0, 0, 1, 1, 0, and 1, 1. And these coefficients are always going to be plus or minus 1/2. And that means if we take the absolute value squared of these coefficients, we're going to get 1/4. So what is going on with these signs over here? You can see that in this term, we have -1 to the power of xi. That means the value of xi over here, that controls whether we have a plus sign or a minus sign as multiplying this state over here. And over here, the value of zeta is controlling the sign. And in this case over here, we have a more complicated relationship. Here we have the sum of zeta and xi controlling whether or not this minus sign gets switched off. So if zeta and xi are both equal to 0 or both equal to 1, that means we're going to have minus 1 to the power of 0 or minus 1 squared, and that's equal to plus 1. So this will become plus 1. And that means we'll just have a minus sign over here. So this minus sign will be multiplying the 1, 1 state. But what if zeta and xi have different values? If we have 0 plus 1 or 1 plus 0 present over here, that means we're going to have minus 1 to the power of 1, which activates this minus 1, and that multiplies with this minus sign, and that gives us a plus sign. And in that case, we're going to have a plus sign in front of this 1, 1 state. So this is a very interesting way of writing these equations. So when we have this format, where we have this classical bit zeta and this classical bit xi, this allows us to write 4 equations in one equation. So over here, we actually have 4 equations in one equation, and that's present over here as well. So we have a general relationship that works for all 4 of the Bell states.